Hello everyone. In this video we are going to learn about priority queues and which is a type of abstract data type. We will learn about all the operations that we define over the priority queues and then we will see how we can implement it, and through that we will learn about a new data structure which is called binary heaps. Remember at the beginning of this course, we have talked about abstract list, and we saw two different implementation for that using arrays or linked list. So abstract list had a lot of operators, a lot of methods. You can insert an item at arbitrary place at the beginning, at the end, at any specific position that you want. You can remove a method from everywhere that you want, right? So it had a lot of different methods and doesn't actually put too much restriction over that. Then we learned about two a specific form of abstract data types that they are a kind of a list that puts some restriction over the operators that you can, over the operations that are applicable over these abstract data types. A stack and queue. Remember, so a stack and queue, both of them similar to a list, keeps the items in linear order, but the difference is that you cannot remove or insert at arbitrary place. For example, for a stack, you can always just put anything on top of the stack or remove anything from the top of the stack, something from the top of the stack. You cannot insert some at arbitrary place. You cannot insert and change the order there. You can either remove an item from the top of the stack or insert an item to the top of the stack. So a stack is a restricted form of a list. Or queue, remember we have talked about the queue that it has some front and rear, and when you are actually removing from again, a queue will keep the items in linear order, but if you are going to remove from the queue, you have to remove it from the front side, and if you are going to insert to the queue, you have to put it at the rear side. So again, you cannot insert or delete at some arbitrary position in a queue. So both a stack and queue are restricted form of a list. Then we have learned about abstract sorted list, and we have seen the binary search tree and AVL trees as some implementation for abstract sorted list. So again, in abstract sorted list, you keep the items in linear order, but the difference is that you maintain the order of the items. So all the items will be kept in sorted order. So today in this video, we are going to learn about a more restricted form of abstract sorted list, which we call it a priority queue. So as the name actually tells you, this is going to be a queue, but the difference is that you are not going to insert or remove just based on the time of insertion to the your queue, or that's the first in first out. This is not going to be a first in first out. We are going to remove the items based on some metric. That's why we call it a priority queue. So let me give you an example. What is a priority queue and why we need it? Just assume that we are going to implement some application for a printer that manage the jobs that you print on a printer. And assume we got 3 jobs job A has 100 pages to be print, job B has 10 pages, and job C has 1 page. And just consider this fact that your application, that the application that you write for this, for the management of the jobs on this printer, is supposed to minimize the waiting time, average waiting time. So what is the waiting time for any job? The waiting time for any job is going to be the how much time it would take for this job to be done, to be printed, and you get the result. So if just assume that you got these jobs, in the first you got A, then just after a millisecond you got B and C. Okay, so basically when you are going to start doing them, you got all of them, but you know that A came first, then B, then C. So if I wanted to actually calculate the average waiting time, if I do the jobs using the first in, first out policy, so the first job that came in was A, then you should do A, then B, then C. What is going to be the average time, average waiting time for this? So for job A, the waiting time is going to be how much time it would take to print the job, the whole job, because you are not going to wait for anything else to be done. But you have to wait until all of the pages in this job should be printed, right? And just assume that for each page it would take some unit of time. Doesn't matter how much, but just some time units. So 100 pages for job A. Then after you are done with job A, you are going to do job B. So you have to wait 100 units of time to job A to be done, then 10 units of time for job B to be finished. So the waiting time for job B is going to be 110. Then after you are done with job A and B, you can do job C, which has only 1 page. So you have to wait for the job A and B to be done, which is going to be 110 units of time, then 1 more unit of time to finish printing job C. So the waiting time for job C is going to be 111. So the average waiting time, in this case, it's going to be just, you get the average between these 3 numbers, right? So which is going to be 107. So let me actually just give you another order that minimizes the average waiting time. Instead of printing the jobs in the first in, first out policy, I can start, and if I have 3 jobs, or doesn't matter how many jobs I have, I wanted to just take the shortest job, get it done, and then go to the next job. So in this way, the first job that will be printed is going to be C, which is the shortest one, right? So for job C, the waiting time is going to be 1, just 1 job, and it hasn't been waiting for anything else. For job B, you have to wait for job C to be done, and then 10 units of time for job B, so it's going to be 11. And for job A, you have to wait for 11 units of time for job B and C to be done, and then 100 units of time for job A itself to be printed. So its total is going to be 11 and 100. If we get an average over these 3 numbers, you get 41 average of the waiting time, which is way lower than first in, first out policy. Okay, so now you can see that again here I need a queue, but the queue that I'm working on, I want this queue to just whenever I'm removing something from the queue, I want that to return the job which has the shortest length, right? So I have defined a different metric. This is not just based on the arrival or insertion to the queue. It is based on some other metric. That's why we call it a priority queue. We define another metric and always wanted our queue to give us the item with the highest priority. That here the priority has been defined based on the length. So the shorter, the higher priority. This type of abstract data type is called a priority queue. So what are the operations that we have for our priority queue? The operations are going to be very similar to what the name of them are going to be the same name as the operators that we defined for the regular queue. You have a method that we call it top or peak that just tells us what is going to be the most priority item. The item with the highest priority in the queue. It's not going to remove it. It just tells us that what is the item with the highest priority available in the queue. Popping and pushing. So popping is going to, I forgot to make it bold. Let me actually make it bold here. So popping is going to pop the item with the highest priority, just remove the item. And pushing the items, just inserting an item into the priority queue. So here the thing is, in our priority queue, if you have two items that has the same kind of priority score, because you can see that we should define some metric that gives us the priority queue, the priority score. And if you have two items that has the same priority queue, that item that came first is going to be removed first. So we will keep that first in first out policy, but we will apply it just over those items that has the same priority score. If your items, for example, if you have, so now you can see that you can have repetition. For example, you can have two jobs that both of them has only 3 pages to be printed. So they have the same priority score. You would give if you are removing one, you are removing the one that has been inserted earlier. So first in, first out. So one thing about before we jump into the implementation, one thing about the items that you can store in a priority queue is that your item should be comparable, right? Basically, it means that you should have some metric to compare the items based on that. All of your items should have some key that based on that key you will say, okay, this item has a higher priority than the other item. So it's just a matter of the implementation. Just make sure that all the items that we insert in our priority queue should be comparable. Exactly like what we did for the binary search trees. That if you are inserting an item into a binary search tree, that item should be comparable. So it should have some key that we compare the items based on that key. So now we have defined the specification of the priority queue, the methods that we need, right? And now we wanted to actually see that what is going to be the best core data structure that we can use. Array, linked list, maybe a tree. What can we do, right? So the first option that might come to mind is that, okay, how about using a linked list or an array? The issue with the linked list, remember, for example, for a regular queue, we could either implement it using a linked list or arrays. So this is the first option that came to mind. Okay, just like a regular queue, let's use a linked list or an array. That's not, there's not much difference between these two. So if you have a linked list, inserting to your the linked list is going to be done in constant amount of work, right? You can actually just always insert to the beginning of the linked list or to the end of a linked list. So push can be done in constant amount of work time. But how about pick or pop? In pick and pop, you are looking for the item that has the highest priority, right? When I'm actually inserting an item, if I always just add the item at the end of the queue, for example, end of the linked list, if you are searching for the item with the highest priority, you have to look at all the items in your links to find the one that has the highest priority and just return that. And you can see that the time complexity for both pick or pop is going to be linear. Finding the item with the highest priority in a regular linked list, it is going to be linear because you have to actually search for it and remove it. So the other option that came to mind is that, okay, why not using an AVL tree, a kind of binary search tree, right? Because we have seen that abstract sorted list has been implemented using an AVL tree, a kind of a binary search tree, right? So the first thing that came to mind is that, okay, let's just use a binary search tree, an AVL tree. And because we have seen that the time complexity of inserting an item to an AVL tree, removing an item, or adding an item could be done there in log n time based on the height of the tree, and you know that the AVL tree is balanced, so it can be done in O of log of n. And this is exactly what I need, because I wanted the items to actually keep all the item in a we don't really need to keep all the items in sorted order, but anyway, this is something that helps us because we want the item to be processed based on some priority queue. So if I can keep them in sorted way, I always know where is the one with the highest priority. For example, if the highest priority is the minimum item, you always know how to remove the minimum item, and the time complexity is going to be log of n. Inserting to that is going to be log of n, and just checking what is the minimum item is going to be done in log of n. This is good. You can use a binary search tree. But remember, we have talked about the AVL trees that gives us this very interesting and good, the most efficient time complexity. But it was too complicated. Remember, we have discussed about how complicated the insertion was, or in terms of the implementation. I'm just trying to tell you that maybe there is something else that can gives us this good specification that you can insert or remove to your data structure in log n. But it's not as complicated as an AVL tree. And yes, there is a data structure that we call it a binary heap. The point is that if you are going to use an AVL tree, an AVL tree is a very interesting data structure, and it has a very efficient operations. All the insertion, remove, everything can be done in log n. This is very good. But the thing is, in a priority queue, do I need to keep all the items in sorted order? You see that AVL tree, the specification of the AVL tree is that it keeps all the items in sorted order. But if I need a priority queue, I don't really care about the complete ordering of the items. I only care about what is the highest priority. What is the one with the highest priority? For example, what is the smallest? Or what is the largest? That's it. I don't care that how it has stored the rest of the items. I just want it to give me the item, the maximum item or the minimum item, right? So I'm just trying to tell you that exactly like a stack and queue, which has, they are a kind of list, but you restricted the operations, so you get a simpler data structure than a regular list. We didn't actually implement many of the operations. For example, inserting at arbitrary place, we didn't implement it in a stack or in a queue. We just implement inserting to the top of the stack or removing from the top of the stack, right? So here I'm also trying to tell you that AVL tree is very good, but I don't need AVL tree because I don't need to keep all the items in sorted order. So based on that, maybe I can get something with a, some data structure which I can implement the methods in a simpler way. And yes, there is such a data structure, and we call it a binary heap. We have two kind of binary heaps. One is called min-heap, the other one is called max-heap. The thing is, a binary heap is going to be a kind of tree. So you can actually relate to this idea now that a stack or queue was a restricted form of abstract list, and both of them has been implemented using an array or a linked list, right? A binary heap is going to be, a more restricted form of an abstract sorted list. So it is going to be how we implemented an abstract sorted list using a tree, which we call it AVL tree. So for the priority queue, or here we actually call this binary heap, we are going to use a tree, right? But this tree is not like AVL tree. It has less restrictions over the shape of the tree. I'm going to give you the full definition and more example. So a binary heap is going to be a tree. In fact, it's going to be a binary heap. And we have two kind of the binary heap. One is called min-heap, the other one is max-heap. The point is, in min-heap, always we give the priority to the smaller items, and in max-heap, we give the priority to the larger items. Okay, so what is a binary heap? All of the definitions that I'm going to give here are going to be for the min-heap. Okay, but you can just reverse the definition and it will be the max-heap. So there is no difference between max-heap and min-heap. The only difference is that you give the priority to the smaller items or to the larger items. So I'm going to stick to min-heap. What I'm going to define here and all the operators is just for min-heap. If you reverse the order, it will be a max-heap. So there is not much difference between them, just the give the priority to the smaller ones or to the larger one. So what is a min-heap, a binary min-heap? We will say that a non-empty binary tree, so binary heap is going to be a tree, and it is a binary tree. So the name binary heap is actually telling you that this is going to be a binary tree. A binary tree is a min-heap if the element that you keep in the root is going to be the smallest element among all the items that you have in the whole tree, and this property actually holds, you have the same property over all the nodes in the tree. So basically for every node, the item that you keeps in that node you keep in that node is going to be the smallest item. This is a min heap, the smallest item among all the items in that subtree. Okay, so you can see that when I'm actually checking this part, the thing is the root, I know the root is 0. Okay, I don't care that, for example, I have some items here greater than some items here on the left or right. The only thing that I care is that 0 is the smallest item among all the items in the tree. Then over the left subtree, I don't care that if there are some items smaller or greater on the left side or the right side. The only thing that I care is the value of this node is the smallest one among all of the items in the left and right. Over the right subtree, the same. The value of the node, which is the root of this subtree, is going to be the smallest one among all of the items in this subtree. So this is very important. This is the main difference between the binary search tree and binary heap or min heap. In binary search tree, you would say whatever is in the left subtree should be smaller than the value at the root, and whatever in the right subtree should be greater. So you give a complete ordering over the numbers. But here, I just care that the value at the root is the smallest one among all the items. So for every subtree, the value at the root of that subtree is the smallest one among all the items. This is very important because this makes actually, most of the time, if you're confused about binary heap, binary search tree, and binary tree, it just comes from this definition. Okay, just make sure that you get yourself familiar with this definition. Let me actually give you some example. This is a binary heap, which is a min heap. If you look at any of the items, any of the nodes in this tree, you will see that that node has the smallest item among all the items in the corresponding subtree. For example, for the whole tree, the value at the root is the smallest one among all the items on the left and right subtree, doesn't matter where. So, or for example, if you look at this item, this is the smallest item among all the nodes that you have on the left or right. This is the smallest item among all the items in the left or right. There is nothing on the right, so everything you just compare for the items on the left. This is the smallest item among all the items in this subtree under this node. This is the smallest item among all the items here. Okay, so again, you see that binary heap, just like the binary search tree, doesn't put any constraint over the shape of the tree. So this, you can see that, for example, this is not like an AVL tree. This is not balanced. On the left, this looks more full. On the right, for example, you can see that here you don't have any node. On the right of 12, there is nothing. So binary heap doesn't put any constraint on the shape of the tree. Although later on we will actually see that if we don't put any constraint on the shape of the tree, we cannot get the time complexity of log of n. Remember, this is exactly the same issue that we had over the binary search tree, that if you don't put any constraint on the shape of the tree can be, for example, something like this. This is a This is also a binary heap, right? The smallest item is at the root, but this is not like a balanced tree. And the time complexity for insertion and deletion in the binary tree that you have is going to depend on height of the tree. And if you don't put the restriction over the height, it can be as worse as n. And if you actually make it balanced, this can be log of n. So we wanted this, but I'm going to actually just come back to the implementation and how we can make sure the tree is going to be balanced. How we can implement a binary heap and make sure that a specific form of binary heap and make sure that is going to give us the theta of log of n as the height of the tree. So let's forget about the how to make sure this is balanced and just stick to the binary heap. I wanted to actually review the operations top or pick, pop, push, and see that how these operations are going to work over a binary heap. The first method is top or pick. We wanted to have access to the item with the highest priority in a binary heap, in a min heap. We know in our binary heap, which is a tree, the value at the root is going to be the one with the highest priority, the minimum item in the tree. So access to the root is constant. We can actually execute and implement the method pick or top in constant. The next method is pop. We wanted to remove the item with the highest priority from the binary heap. How we can do that? If you actually get the item out of the root, for example, we wanted to remove 3. So there will be a hole in the tree, in the root, right? We have to fill it to make sure that we maintain our binary heap, we maintain our min heap. So the next item that should be replaced in the root is the item, it is going to be the next item with the highest priority, the next minimum item. Where can we find it? You know that the whole tree is a min heap, so over this subtree, the minimum item is going to be stored at the root of this subtree. And again, on the other side, the minimum item on the right side is going to be stored in the root. And this is going to be, this value on the left side and on the right side are the minimum items on the left and right subtree. So to find the minimum item among all of the items, I just need to compare them and get the one which is the smallest. So here it's going to be 7. So you have to copy 7 in the root. And you see that this is just a recursive procedure. You remove 7 from the left side, you copy it at the root, and you recursively apply the same procedure on the left side. 7 will be copied to the root. Again, to fill this hole, you have to look at left and right children, compare them, get the one with the minimum value, that here is going to be 9, so 9 will be copied here. And you actually again repeat to fill this hole to replace actually the position of 9. You have to check the left and right subtree. The minimum item this time is going to be 19. You copy that there, and then you will fill the position of 19. Here you copy the left and the right children. The minimum one is going to be 55. It will be copied here. And you see that the previous position of 55 is a leaf node, right? So you remove the leaf node without any issue. The whole tree is going to be a min heap, a binary heap. And then at the end you will just return the value of the root that you have actually kept. So let me actually show you another step of the pop, just as an example to make sure this is you understand it properly. Assume again I'm going to remove, I'm going to call the pop over this binary heap, a min heap. So 7 was the value of the root. You copy that and you wanted to actually remove it. Then you compare the left and right subtree. Here you compare the left and right subtree. The minimum one was going to be 9, so you copy 9. And then you compare the left and right subtree. The minimum one is going to be 19. You copy that. Then you compare the left and right subtree. The minimum one is going to be 33. It will be copied. And then 33 does have just one child, so that's going to be the minimum one. It will be copied, and this is going to be the result. If I'm going to apply the pop one more time, again, just as an example, if you apply the pop over this subtree again, 9 will be removed. Then if you compare the left and right subtree here, you will see that, okay, 12 this time will be copied, the right subtree. And among the left and right subtree of 12, you see that there is nothing on the right side, so the value from the left will be copied. And then instead of 15, 41 will be copied, and instead of 41, 42 will be copied. This is going to be the final shape of your binary heap. I think now that's clear that how the pop is going to work. And what is going to be the how we can actually insert an item. So in fact, we can do the push in two different ways. We can either start from the root and try to actually, the item that you get, maybe this is going to be the smallest item, right? You can compare it to the root and see that, okay, if it is smaller than the root, you would replace it in the root, and then you try to actually insert the root. It's just like you are pushing the root down in the tree. You want to actually just push it in the either left or right subtree, and you actually just continue. So either you do it, or the other way that I'm going to actually show you is I will insert the new item as some arbitrary leaf node. So here, just take it from me as we just find some arbitrary position that we can have it as a leaf node and insert the item, and then we try to just push the item in the tree to the top, so we find actually the correct position for that. Let me show it to you over an example that makes it much easier to understand. Okay, assume in the previous tree that we had something like this, we wanted to insert 17. And where to insert it? A leaf node, arbitrary leaf node. So for now, just assume that I have randomly find this position here, which was a potential position to insert a leaf node. Later on, I will tell you, because when we are implementing, we cannot actually just take any leaf node position. I will show you how we find the position to insert the item. But for now, just to get the idea, just assume that we find some position, some leaf node position, insert that item. So 32 didn't have actually a left child. So I'm going to insert 17 there. Then, because 17 might be smaller than its parent, 17 was not in the tree before. So I have to find the correct position for 17. I compare 17 to 32, its parent. If it is smaller than its parent, I am going to switch the value of at this node 17 and 32. Because it is smaller than its parent, right? And it cannot be smaller than its parent. So I'm going to actually swap them. Then you continue, again compare 17, the value at here, and its parent. If it is smaller, you swap them. And you can see that I don't need to be careful and care about the sibling. 17, you don't care that if it is smaller or greater than 58. The point is that if 17 is smaller than the parent, so I'm going to swap it. And I don't need to be worried because already I know that whatever is on the right side or left side, it's going to be greater than the parent. So definitely that's going to be greater than 17 as well. So you just compare it with the parent. After you swap them, then again you compare it with its parent. Is it smaller? Yes. So you continue and swap them. And then you compare it with its parent again. Is it smaller? No. So you stop. Okay, you see that for push, you just find some arbitrary leaf node, you insert the item there, then you start comparing with its parent and swap until you find a position that the item is greater than the parent. This is a min heap, right? The item is smaller than the parent, so you would stop. So that's it. That's the result after inserting the item. So this procedure that you compare, you see that we have done something similar. When you are removing, popping an item, or when you are actually inserting an item, you do the comparison with the children or the comparison with the parent. So this procedure that you insert an item and you compare it with its parent, and it's just like you are pushing it up, it is called percolation. We are moving the item up, and this procedure is percolating up in the tree. So you try to actually, you move it up, so we call it percolating up. So we have talked about all the different methods here over a binary heap, over a min heap. Now, if I actually just go back to any of these methods, you will see that the time complexity for example, push was going to be theta of height, right? You started from a leaf node and you just compare and swap with the parent until you find the correct position, and at most you will reach to the root node, right? So the time complexity would depend on the height. About the method pop, also the time complexity would depend on height. It is going to be theta of edge, height, right? Because you remove the item from the root and you compare the left and right values, get the one which is smaller, and you just recursively do the same procedure until you reach to a leaf node. This is exactly going to be the height of the tree, right? So the time complexity of pop is going to be height. The time complexity of top was constant, and I'm not going to actually just go back to that. So now you see that both pop or push would depend on the height of your binary heap. The definition of the binary heap, the way that we define it, doesn't put any restriction over the height. So how can I force the shape of the tree to be in a balanced form? This is going to be the next step in the implementation. So one way to do it is just like the way that we define the AVL balanced for binary search tree, we can define a similar balanced definition for the binary heap and apply it. Okay, so but if we do that, this is going to be something similar to the implementation that we did for the AVL tree. This is correct, you can do that, but I wanted to show you that we can do something much easier using, for the binary heap. We can implement binary heap using much less space and complication. So I am, instead of using a general tree, the way that we implement binary search tree, binary tree, or AVL tree, I am going to implement binary heap, which is a tree, using an array in a form of a complete binary tree. I'm going to show you that, in fact, it is possible that you can implement binary heap using different type of data structure. Implement it to always make sure this is a complete binary tree, implement it to work like a leftiest heap, a skew heap, and Fibonacci heap. These three data structures are more complicated data structures. They have very interesting properties, but they are beyond the scope of this course, and I'm not going to actually discuss them here. Just know that it is possible to implement priority queue binary heap in many different ways. We are going to cover the first one, how to implement a binary heap to make sure that it is always like a complete binary tree. Okay, the shape of the tree is going to be exactly like a complete binary tree. So, and we already know that for the complete binary trees, the tree is balanced. The time complexity, the height of the tree will be log of n, theta of log of n. And remember what was a complete binary tree? Let me actually show you. This is a complete binary tree, right? Remember, it was like a perfect binary tree, and if you had the number of nodes is not exactly 2 power n minus 1, you can start actually filling all the levels from the root one by one, all the levels until the last level, and you fill it from left to right. So here I have 16 nodes, so this is going to be a complete binary tree. If you had one more node, you should actually put it here to make sure this is going to be a complete binary tree. If you add one more node, you should put it here. If you add one more node, you should put it here. So you create a complete binary tree by adding the nodes level by level and from left to right. And I'm going to actually show you that we can create a binary heap and we can keep our tree in a shape of a complete binary tree. That's really interesting, and later on we will see that it would be even more interesting when I show you how we can store this complete binary tree in an array instead of implemented it like a linked list, having a node, have two references for the left and right, and all of those details of the implementation. Instead of that, we can store this tree in an array, and that makes it actually very interesting. So just one thing, the methods, all the methods that we have discussed about, top or pick, pop, and push, we are going to see that how we can adapt them to make sure they are applicable over a complete binary tree. If we apply those methods that we discussed over a complete binary tree, after we are done, the tree should be a complete binary tree again. So the two main methods that we have here are going to be push and pop. For top is not going to change the shape of your tree, so that's not the problem for us. The first method is going to be the method push that I'm going to cover. Remember, for the method push, I said we find some position as a leaf node, some arbitrary position as a leaf node, and you add a new leaf node to the tree, put the item there, and percolate it up. So now if your tree, if your binary heap is in a form of a complete binary tree, you cannot put your item as an arbitrary leaf node. The only position that you should put it, it's going to be after, we fill a complete binary tree level by level and from left to right, right? So if I have a tree like this, the only valid position that I can put a new item, it's going to be here. It's going to be the right child of 36. You cannot put it anywhere else. If you put the item here, the result is not going to be a complete binary tree, right? So in this way, we make it actually unique. So if you want to push an item in your tree, you know where exactly you have to actually put the item. And the rest of it is going to be just like before. You put the item here, then you compare it with its parent, swap if it is a smaller, compare with parent, swap, compare with parent, swap, until you actually find the position. For example, if I insert 25 into this complete binary tree, which is a binary heap, you compare 25 with its parent, this is smaller, you swap it. Then you compare it with its parent, it is smaller, then you swap it. You compare it with its parent, it is not smaller, so you would stop. You would stop here. So you see, after inserting 25, the tree is a complete binary tree, and it is a binary heap as well. All the nodes are going to be smaller than the values in the corresponding subtree. So now I'm going to show you how we can implement pop. The way that we explained pop before was you actually take the item from the root, you copy it somewhere, then there will be a hole in the tree, right? Then you fill it by checking the left and right subtree, find the minimal one, and actually just copy it there, right? So if I apply pop the way that we actually discussed it, this is going to be like this, right? At the end, I will have a hole in the tree. You don't know that the final leaf node that you will remove, where it is going to be. It's so here, after removing the 12, if I apply the previous procedure, the leaf node that will be removed is this one. And you can see that if I remove this node, the tree is not a complete binary tree anymore. So what can I do in this case? So this procedure is going to be very complicated if I do it in this way. Because if I wanted to actually make sure the tree is a complete binary tree, I need to fill this node. What can I do is I can remove, in fact, the only leaf node that can be removed to make sure the tree is a complete binary tree after removing is going to be this position. Right? If you remove this leaf node, safely the tree is going to be a complete binary tree. One thing that I can do is just copy the value of 36 and put it here. But if you copy 36 there, you are not sure that it is smaller than its parent. It is actually greater than its parent. So after copying 36 here, you will see that, okay, the value of 36 is smaller than its parent, and you have to actually start, percolating up. Not only when I remove 12, I actually just remove the items and go to to a leaf node. No, I might actually need to start percolating this value, the new value that I removed from this leaf node, to percolate it up, right? So I'm going to show you a trick. Instead of copying 36 to this hole, I am going to copy 36. I mean, in the original actually case, instead of actually creating all of these holes here, I just removed the item as the last leaf node and copied into the root value, the root position, and then percolate it down. So in this way, I just need to do the procedure once. I need to just go through the tree only once. So the idea is that you get the value, the previous value of the root, keep it somewhere like 12, then remove the very last leaf node, copy the value to the root position. But this item probably, I mean, most likely, this is going to be one of the largest item in the tree, right? You have to percolate that value down. Then, but after you percolate it down, the shape of the tree is not going to be changed. You need to just actually compare the value with left and right subtree, and this time you are just exactly doing that procedure of that we do in the push, but the reverse of that. You are going to percolate down. You compare the node 36 with its left and right subtree, whatever left and right children, whatever is smaller, you swap with that. Then you compare with its children, whatever, again here, you can see that 36 will be copied here. Then you compare the left and right children, which one is going to be smaller, you actually going to swap. And then you compare this position with the left and right subtree, both of them are greater than 36, so you will stop. So this is going to be the method pop. In method push, we insert as the very last disposition, we add a new leaf node, then we percolate up. In the pop, we remove the last leaf node, put it as the root, and then percolate it down. So this is going to be the result. The tree is going to be a complete tree, a complete binary tree, and this is going to be a binary heap as well. All the nodes are going to be smaller than all the values in the corresponding subtree. So this here shows another step of the pop. For example, you apply pop again, so 15 will be actually removed from the root. Then you remove the last leaf node, which is this one. You copy the value as the root, then you started percolate it down. You compare the left and right children, the smaller one, you swap it with the smaller one. You compare the left and right, compare the smaller one, and if it is a smaller, greater than the children, you swap them. So 88 will be copied there, then it will be copied here. Then you compare the left and right, so 88 will be end up to this position. And the tree would look like this. This slide shows another a step of popping an item. So if you call the pop over this tree again, 17 will be removed from the root. The last leaf node is going to be this node here. 53 will be copied to the root. Then it will be percolate down. So you can see that it will actually end up this way, which is going to be the result. This node has been removed here, the previous 53 to the root, then it percolated down, and the tree would look like this. Another step of pop, if you call the pop, the last leaf node is going to be this one, right? This will be copied to the root, then it will be percolated down, which actually will be end up here in this node.